Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Welcome, or hopefully welcome back, to another episode of the Reliability Matters podcast. I'm so glad you're with me today. For those of you who are keeping track, this is episode number 123. We all strive to build products that are reliable. If you're listening to or watching this podcast, chances are you're concerned about reliability, or at least interested in reliability as a subject matter. Where does reliability start? Who is responsible for reliability? What types of reliability testing can be performed? What is HALT? My guest on this episode will help answer these and other reliability-based questions. And my guest is Dr. Christopher Jackson. Dr. Chris Jackson is a leader, engineer, and logistics specialist who has helped many organizations work toward realizing business goals through improving the reliability of their products and processes. He is co-founder of the online training company IS4, founder of Acuitis Reliability. He established the Center for the Safety and Reliability of Autonomous Systems, or SARAS, at UCLA after retiring as a lieutenant colonel, having served 17 years in the Australian Army, where he was the senior reliability engineer. See a theme here? Chris authored multiple reliability and management textbooks and teaches both professional education courses and postgraduate courses. Industries he's helped have ranged from small satellites through military vehicles. Chris is a certified reliability engineer through the American Society of Quality, a member of the Institute of Engineers, Australia, and a chartered professional engineer. Chris was a guest on my podcast back in June of 2020, and I'm thrilled to have him back here today on episode number 123.
Thanks for having me, much appreciated.
Well, thanks for coming back. I guess it wasn't too bad the first time, or you have a short memory, one of the two.
Or it took two years to get over it.
Well, that's 2 years of therapy. Yeah, there you go. That's a very fair statement. So let's start off with this. I want to kind of put reliability in some kind of maybe comedic perspective. Watch this, and then we'll come back and talk about it.
Franz, could you try to break this glass, please? Oh my God. Well, maybe that was a little too hard. Sure. Oh man, it didn't go through.
So Elon Musk introducing his Cybertruck, boasting about how shatterproof and bulletproof the windows are. And to demonstrate that, takes a metal ball and has a stagehand throw it at the window, and of course it shatters immediately. And then he says, well, you probably did it too hard. He lightened up his throw, did it again, shattered again. I don't know if he regrets not doing some type of reliability testing before, or if that was live kind of HALT testing in a very strange way. But,
yes.
but that is what we do not want to see in all of its manifestations when we put product out into the field, right? That's kind of the whole idea of reliability testing.
Yeah, and I think, I don't know, it's hard to imagine there was absolutely no reliability-related testing for that.
Well, there certainly wasn't a steel ball test. There was probably a bullet test. I'm sure when he said it's bulletproof, they tested it, but he probably didn't think of testing it with a steel ball, right?
I can't help but think there was some sort of test, and perhaps they had sort of, the stand, inadvertently put the stand in, or prototype glass. I don't know. It's just hard to believe that that would be the first time a steel ball would ever be thrown at those windows. But stranger things have happened. But it sort of isn't a bad lead into what we're talking about today, HALT, which is essentially pushing something not only to, but beyond its limits to work out its weak points.
Yeah. There's a lot of confusion by some, not by reliability experts, but by people building things that aren't necessarily reliability experts, about the difference between quality and reliability. In our factory, we had a long talk with a supplier when a certain product started to fail in the field, or a component of that product started to fail in the field. We addressed the issue with the supplier, and they told us of how much quality control they have in their product, and the product was it was a crimp failure, and the crimp was the proper crimp. It was crimped to the proper torque or pressure settings, and they assured us it met all these quality standards. Yet it still failed, and it failed repeatedly. So, explain to me and my audience from your 35,000-foot view the difference between quality and reliability.
Well, I'll be honest. I think the only reason you want to have a difference between those two terms is if it's going to help your organization. So obviously, you're talking about scenarios where there is quality is analogous to manufacturing adherence to tolerances and specifications, and any deviation from what has been asked for represents a reduction in quality. And I don't disagree with that definition, as long as that definition helps. There are scenarios where you could describe products which are low quality because they're hard to use, they're not user friendly, they're not pretty to look at, they they have inexplicable demands on the user in terms of trying to, for classic example is medical devices or medical test things where you need to, some are just much better at allowing the human-machine interface to interact with in a more intuitive way with the technician than others, even though that's outside the sort of manufacturing specific definition of quality. So my personal opinion is I use the term quality to use the definition that best helps that organization organize its thoughts. And so if defining quality in terms of, from the perspective of manufacturing defects, helps sort of pigeonhole certain problems so we can go to the right team to talk about solving an issue, that's fantastic. I've seen, however, in other circumstances where that definition is used with religious zealotry to the extent that no one else thinks about quality during design or human-machine interfaces, to the detriment of perceived quality thereafter. So the difference between quality and reliability traditionally is essentially failures that are caused by manufacturing defects, or those deviations outside of tolerances, are classified as quality failures, and those that are associated with wear out are classified as reliability failures. Technically, there is no distinction because reliability deals with the probability of failure regardless of the cause. And if it helps to solve problems by having that definition in an organization, run with it. But if it introduces, arbitrary internal arguments about accountability and blame, then the definition is probably not helpful. Is that anywhere near sort of answer you were after? Yeah.
The way I think of it, and this is kind of this isn't the specific problem we had, but this is kind of analogous to it. I'm sitting in front of a MacBook Pro, and I'm sure that I'm kind of a Mac head. I like Apple products, right. So I kind of believe everything is built maybe a little better than the lowest end PC or whatever, and I'm sure they have reliability or quality standards and things like that. However, if I took my MacBook Pro and put it into the swimming pool in my backyard, 100% of the time it would fail. Now, does that mean the quality was bad? No, the quality, they hit the mark on every single component, every single crimp, every single solder joint, etc. It was never designed to go into the water. And that was the problem we were having with this particular part. Although it was hitting all the marks for their quality control, it was built properly, it was crimped properly, the materials were the proper materials. Its use was outside of its intended, purpose, and that maybe is where testing, reliability testing in extreme environments would come in. In my world, I'm in the cleaning world, right? My expertise is in contamination. Never a hit at a cocktail party when people go, "What do you do?" Well, I'm an expert in contamination. Yeah, that'll clear a room to the bar, right? If you want to get to the bar, to the front of the line, just tell people what you do. The C's part.
So that's That's a good one to look away on.
Right, exactly. In my world, it's harsh environments that exacerbate electrochemical migration issues because they react with the conductive residues on a board and bad things happen. So in our world, to evaluate how clean something is, we have to actually test it in harsh conditions because it seems clean until it's in a harsh condition. And then all of a sudden, it's the MacBook Pro in the swimming pool. So in our industry, we have to test under the most extreme conditions, even if the part isn't intended to go into those extreme conditions. Electronics are mobile. It could. So, we have our little, it's not HALT testing specifically, or at least by name, but we have our version of HALT testing just within cleanliness quantification.
I think it's an important topic. Misuse, abuse, vandalism, whatever you want to call it. I was teaching a course last night to an Australian audience, and engineers tend to go very quickly towards, if the customer's using outside the intended design specification or operating protocol, insert taxonomy for your industry there. It's been my experience that most customers aren't trying to break anything. They are just using something in a way that suits them, which might not suit the vision of the engineering design team, the software engineers, what have you, at the very start. I use the example of cell phones or mobile phones that were originally designed late 1990s to be luxury items, but the demographic, or not the demographic, the market segment which actually took them to the next levels were tradespeople. So the plumbers, the electricians. And the reason why is because before cell phones or mobile phones, a plumber would go to a job, drive back to the office, work out where they had to go next, and off they go. And these very expensive bricks saved time and money in regard to not circumventing having to go back to the office, especially if the next job was next door. And so there was the proliferation of mobile phone, cell phone companies who were coming up with these bricks. But because the market essentially demanded that these be thrown in the toolbox, hypothetical toolbox, in some case literal toolbox of a plumber, the only companies that survived were those that built mobile phones, cell phones, which could survive that environment. Now, one engineer would argue, they're using outside the design specification or the intended use. And you go, that's your intended use. You're not the customer, you're the user. They're not abusing it. They're not trying to.
Right. There's the intended use, and then there's the practical use, right? And you have to build for the practical.
Exactly. And that's customers and users only pay money for practical things. So if your thing isn't practical anymore, then it's not going to be a bestseller. And so I think with HALT, highly accelerated live testing, which is often it is a scientific, but in many cases brute force way of taking a prototype and not only pushing it to its limits, but pushing it beyond its limits. And the main reason you do that is not to demonstrate that it can work. You are trying to find out what the weak points are. Because most design challenges, if you introduce a corrective action into the first design or the second design iteration very, very early on, they're borderline free, because it often just means some simple rerouting of a cable or moving a capacitor from here on that PCB to over there, or instead of using solder joints, you use sockets. But of course, you can't modify PCBs you've received from a supplier to have those things moved around. You have to go and reorder a whole new fleet of them. So if you can work that out at the very start, and so that you have the right dampening, you have the right sort of distribution across the PCB in particular for vibration. Just think about all the times we drop those cell phones and mobile phones these days. Then those simple changes are borderline free, far simple and free is the term I like using, if you can identify them early. And that's where HALT comes in, because it's going to break your prototype or the component you're testing several times over, but the intent is to work out which bit breaks first and then which the next bit that breaks, so on and so forth. because
Sure, I'd imagine also it's a good benchmark for where things break. What is the breaking point, right? So you could set up the expectation to be somewhere under that breaking point. We're going to get into the specifics a little bit, but let's define some terms. Most of my audience is within the electronic assembly space, and which comes in very handy because you did a webinar recently where the example that you gave was on a device that had a printed circuit assembly in it. So that works out perfect. So I watched that webinar. I took some notes, and we'll kind of use that webinar as a guideline for this conversation, because it's your example. I know your reliability expertise goes well beyond electronics, but your example was electronics, so it was perfect for this conversation. But not everyone in my audience is familiar with HALT, and not everyone in my audience is within the electronic space. So let's just define a few terms. Tell me what, first of all, ALT is, without the H, and HALT. Those are both reliability tools. Tell me the difference between ALT and HALT, besides the H, and then just describe, kind of in a 30,000 foot view. We'll dive into it in a little bit, but what HALT is.
So I think the best way of describing the difference is what each test provides as an output. So HALT is intended to give you a prioritized list of the weak points of your system or your component. So number one might be capacitor over here. Number two might be solder joint over there. So the output of HALT is a prioritized list of weak points. When I say prioritize, the weakest part of your thing is at number one. The next weakest part is at number two. ALT, even though it has one letter different in its acronym, is very, very different, because the outcome of ALT, accelerated live testing, is a quantification of the time to failure, or the likely time to failure, for a particular way that your product's going to fail. So, for example, accelerated live testing might involve trying to understand how long it's going to take before corrosion causes your product to fail. And you do that by increasing the stresses that accelerate corrosion, but in a scientific way. So you need to have an underlying model of how corrosion propagates throughout something. And then you say, okay, well, if we turn the temperature and humidity up to this much, then 1 day worth of accelerated live testing is equivalent to 3 years of real world conditions. So you can, in 1 day, replicate 3 years of use, and therefore have a much shorter test duration, but still characterize reliability and time to failure in the order of years or decades in some cases. So that's the fundamental difference between HALT and ALT. HALT, prioritize list of weak points, starting with the weakest point. ALT is a quantification of how one particular way your thing's going to fail is going to affect time to failure.
Excellent. Thanks for that explanation. Let's get into an example that you gave. To me, this was a good vehicle to understand better HALT testing, and we'll just start drilling down in it. We don't have 4 years to go to a degree level on this, so let's make the best time that we can. Let's make the best use of the time that we have. So let's start with the example you gave of a smart lock. A smart lock, would be these electronic door locks that you would find in residential doors and maybe commercial doors that allow you to open it or unlock it with your cell phone or a code or whatever the case may be. You gave a really good example of a HALT. It's really funny, HALT. I always want to say HALT test, but what I'm saying is highly accelerated, reliability test. I'm using the test twice, but it just sounds funny to leave it on its own. So I'm going to defy grammar. When I say HALT, I'm going to say a HALT test, even though I'm saying test in a row.
Like an ATM machine.
Exactly. Yes. I worry about things I shouldn't worry about, but that's one of those things that just bothers me. But so this was a good example of a HALT test, and because it demonstrates what we talked about earlier as we opened, which is kind of maybe unintended uses or environments outside of the predicted norm, right? It was a good example of that, door slamming, things like that. So walk me through the smart lock and the various, components of it that were going to be tested, and then the kind of the awakening, the results of that, what it showed. Let's just kind of go through it.
Right, so I'll go way back to the dawn of time with that smart lock, because I do a fair bit of fair bit of training, and I needed to have an exemplar product or system for all my courses. And after much surveying and much introspection, it was the smart lock I came up with, because it appeals to electronic assembly specialists like yourself. It also appeals to mechanical engineers because it has an electric motor in it and gear sets and things like that. It obviously is very reliant on software. Aesthetics are important. It needs to interface with doors and things like that. So it's got a little bit of everything for everyone.
Check. Yeah.
Right. And of course, about half of all failures occur at interfaces. And, well, you got smart lock technologies that are, which are so disparate that they need to work together in a harmonious way. So it's another check. And so I essentially, with a couple of experts, created a completely unique smart lock, so I didn't have to worry about proprietary information. It's my smart lock. It's something that I can pull apart and describe and say what happens. But I'm able to draw in sort of experiences and anecdotes from real world scenarios and apply it to this smart lock. And in this smart lock, one of the things you talk about door slams, and that's a classic case of an opportunity for you to misjudge how your thing is going to be used. Of course, when we think about shutting a door, the normal way you close a door is quite controlled. But if anyone is married, or if anyone has children, or if anyone lives with wind, from time to time, that door is going to be slammed. And that's just the way it is.
Happens.
Now,
hypothetically, it happens, yes.
Right, and engineers can often complain, well, that's if it fails, it's a customer's fault, therefore it's not ours, and you're missing the point. They're not interested in something that's so flimsy that it's going to not work as soon as there's a door slam, and door slams will occur. And how will you demonstrate that it failed due to a door slam? And insert rabbit warren there. And so it's just a good example of just making sure the people on my course are not thinking about the perfect customer who shuts the door with the delicacy of a butterfly wing every single time. That's just, that customer does not exist. Or if you try to cater for that customer, you're going to go broke pretty quick.
It'll be at the exclusion of all the others. Yeah.
Right. And so one of the parts of a smart lock is obviously at least one printable circuit board, PCB, with all sorts of components on it. And I went through an example where we thought, well, let's think about what we can do before we design it to make this thing more reliable, because it's very overwhelming at the start of a design process, or where you say, okay, let's try and design failures out of this thing before you've even designed it. People almost immediately get overwhelmed by that, and that's unfortunately how many reliability engineering so-called masters and greybeard tend to spell reliability engineering, the bottom-up approach. I hate that term because it means you need to predict every single failure mechanism and do something about it. Good luck with that. Never once has worked. But we just looked at an example where the initial idea involved cables or wires being soldered from the electric motor and then being connected to the PCB also by solder joints. And if we use, something like a FMEA or fault tree analysis, just to think about it, then the idea is that it's not hard to realize that solder joints are not super strong structurally, and then what can we do to address it? And then there's a number of corrective actions you can come up with to embed in your first design, like using thicker gauge wire, having shorter wire that accumulates less momentum during the door slamming events. You have those wires physically secured to the chassis or frame of the smart lock, so that momentum is dissipated, or kinetic energy is dissipated not through the solder joints. And then another corrective action is to use a socket and plug at the PCB and not a solder joint. And that obviously has the additional benefit of being easier to assemble. Another idea for corrective action is to add visual inspection on motor solder joints to supplier inspection checklists. And then another one is maybe we'll do a surveillance automated microscopic optical inspection of 10% of incoming motors. The idea is that hopefully with that example, I convince people that we can actually think about or preempt a good number of these design ideas before we start designing with too much fervor. And if we do that, if these corrective actions I came up with are borderline free, they're far simple free if you embed them into your first design. And of course, we're already starting to write our test plan by those corrective actions as well. But then that's all well and good. And if you do that, you're going to have a much more robust smart lock from the very, very start. Then if you look at the PCB itself, we know that PCBs can be susceptible to damage associated with shock loads and vibration. So the example I used was, well, let's just say there's a capacitor on our PCB, and that door slamming event is obviously going to transmit forces to the PCB. Perhaps that capacitor is going to really easily break free. But that is impossible to predict specifically at the initial design phase. You might know PCBs in general and the components that are connected to them are prone to being damaged during shock loading events, but you just don't know which one. And that's where HALT is very, very useful, because you can take a prototype PCB and do things to it and identify, yep, that capacitor is actually going to vibrate free. So what do? All sorts of options. Maybe we add some additional rubber mounts or additional mounting. Maybe there's dampenings. Any number of really simple ideas to make sure that door slams aren't going to ruin the day of that PCB. The difference between those initial corrective actions is they are very intuitive. The final corrective action to have those additional rubber mounts, it's not directly intuitive, because our human brains can't just simply look at a circuit board and work out where vibration and harmonics are going to amplify and destroy that capacitor. But we're smart enough to know that it's an issue, so that's where HALT testing, we'll use your grammatical approach to explaining HALT.
If we're going to be wrong, we'll both be wrong, right? Exactly.
Absolutely. It's a double negative, so positive. So we'll run with that.
I like your math.
Right. So the HALT can work out where those weak points are of your system, which you can't intuitively identify. And fault testing is so fast, and it's obviously not free, but it's very inexpensive, that when you understand what's keeping you up at night with your brand new smart lock or equivalent device, HALT testing can take a good chunk of that overwhelm away. So, that was sort of the preamble to the webinar. We looked at how HALT testing is then implemented in practice, and PCBs and circuitry and electronic components are one of the main elements of systems that are subjected to HALT.
There are testers on the market from a number of manufacturers that are useful in HALT testing. They are, basically torture machines. I think we could extract confessions from people if we had the same type of technology for people. It would probably be illegal, only used at black sites, around the world.
Right.
Walk me through a HALT testing machine. The tester that you used as an example, I know it wasn't an endorsement, but just to put a pin in the map, was a Qualmark Typhoon 4.0. And I'm sure there's a bunch of other brands out there too. And the show isn't about HALT testers. However, it was amazing that types of tests it performed and how it hit a lot of checkboxes within this sample part, the automatic door lock, that had electronic, electrical, mechanical, various substrate materials that all could be tested in this one magic box. So Walk me through a typical or stereotypical HALT testing chamber. What types of tests it performs, and then we'll kind of dive in deeper from there.
Right. So the test chamber you're talking about, Mike, it looks like a large refrigerator, perhaps with a sort of hospital vibe going on with it. But the idea is you have this big refrigerator-looking device, and inside you can open the door up, and you'll see there's like a table, which looks like any sort of table you'd be bolting a bit of metal down to for milling machines and things like that. So you have this table inside this fridge-looking device, and you bolt down whatever it is you're trying to test on that table. And once you shut the door, what the test chamber can then do is rapidly, and I mean really rapidly, increase the temperature up to as high as 200 degrees Celsius, and then really rapidly chill it back down to minus 100 degrees Celsius. And that table, it can have up to 600 pounds worth of stuff bolted to it. And the reason why that's important is because that table then goes through vibration profiles, 6 degree of freedom, random vibration profiles, all the way up to 75 GRMS, which is a considerable amount of vibration. And how this machine does that is with, for example, a liquid nitrogen. It has huge resistors that essentially dumps electricity or electrical power as thermal energy into the chamber itself. And so it's quite a system. The fridge looking part is only part of it. You need to have compression chambers and everything else outside of the building to make it work. And it sounds fairly brutal the way you describe it. It absolutely is. But you don't use it in that way. You often have a test profile, especially for electronic components, which the sort of stock standard approach goes through certain phases. The first one is what's called a cold thermal stress test, where you essentially reduce the temperature one step at a time until it gets cold enough for something to happen. When enough bad things happen, you go, okay, we're done with that. And then you'll have a hot thermal stress test where you increase the temperature one step at a time, perhaps at 10 degrees Celsius steps. And you keep doing that until enough different bad things happen. You go, okay, we've learned enough from that profile. Then maybe you'll go through rapid thermal cycling, where you go from high to low and see what you observe. The next thing you might do is vibration step testing, where you increase the vibration one step at a time, say maybe by 5 RGMS until enough interesting or bad things happen. And then the very last thing often is a combined thermal and vibration test. And the reason why you want to do that is because it's just being shown analogously and empirically that sort of thermal stresses, those sort of thermal stresses, things expand and contract when they get hotter and colder at different rates. And of course, vibration introduces all sorts of weird and wonderful forces to different parts of your system. But it's just been shown that this sort of rapid cyclic testing really mimics many of the vibrations and many of the fatigue cycles that you see through normal use of your device later on. The idea is that as you're testing, when I said interesting things happen or bad things happen, what I'm referring to is a bit of your system or component fails or breaks. You usually stop the test, do a quick investigation, patch it back up, then keep going until the next thing breaks. And so this single test chamber can do all that. The thermal cycling, and the vibration cycling as well, a vibration step test. You don't cycle vibration, just goes up and up and up. And so that's the sort of stock standard HALT testing profile that many people will think of, and it's very, very useful for your domain. But in practice, anyone can create their own HALT test profile, especially for larger mechanical pieces. You just need to envisage your own torture chamber and work out what stresses are going to ruin the day of your particular device, and then off you go. It doesn't have to be in a HALT test chamber. That said, for electronic components, HALT test chambers are pretty useful.
Yeah, I was going to ask you, if someone is on a limited budget and they want to do some type of accelerated life testing, or highly accelerated life testing in this case, do they have to use a test chamber, or can they devise a torture device of their own? Can they improvise? And I guess the answer is it depends, right? That's probably
Right.
not a stock answer for everybody. I would imagine machines that can do plus whatever to minus whatever temperature, that use nitrogen to chill and super effective heaters to heat, and have vibration tables and shock capabilities. They're not $500 machines. They're probably,
Nope.
I would guess, in the hundreds of thousands of dollars. I'm guessing.
Yep.
That would tell me if I'm an automobile manufacturer, I probably have 8 of these machines in my reliability lab. If I'm
Yep.
not that, if I'm a mere mortal, building smaller quantities of things, I probably don't have the resources to put that in the lab, nor do I have the resources to hire an engineer or hire a technician to understand how to operate that machine and interpret the results. Is it your experience that most of these HALT tests are performed by a third-party laboratory that kind of knows what they're doing, or at what point do people bring that in-house, whether it be in with hundreds of thousands of dollars worth of equipment or a homemade test? Where do you see the line is? I know that's subjective, but are there types of businesses that their products are so unique they just have to create something in-house? There is no magic box that could do it, or I'm throwing a lot of different variations of the same question at you here, but I'm just going to turn it over to you. What's your take on sending out to a third party, doing it in-house, creating your own unique set of test criteria, whatever the case may be?
Well, I mean, first of all, the HALT test chambers we described just in this conversation, they're really, really useful across a wide range of products, medical devices, structural things. So I'd argue that most applications of HALT, that test chamber is going to be quite useful. So there'll be fewer and fewer applications, I would argue, where you'd have to create your own device to torture your thing. 9 times out of 10, when you do need to create your own device, it's actually to replicate much of what a HALT testing chamber does. But your thing is so huge that you sort of need to take up an entire garage or a workshop, so you create your own equivalent. But so my experience is that most of the HALT that gets done is outsourced and is to a HALT lab, and that's usually yields good results. But that said, you can't turn off your brain. If you're creating a smart lock, as a rule, you're not going to. It's not going to be worthwhile getting a HALT chamber and then creating a laboratory, because the HALT test chamber is only as good as the technician. So my threshold, as a rule, is: do you have enough HALT work to keep one person full-time busy? It's not money. It's not necessarily down to salary and cost-benefit analysis. It's just that you don't want to have your HALT technician doing HALT once every 6 months, because he or she will essentially lose that tactile experience and not have that corporate knowledge that you want. If you can keep your HALT technician busy year-round, then that makes sense to have someone on site where they can just focus on being the best HALT technician they can be. That's my sort of threshold. If you can't keep someone full-time, happily engaged doing HALT, my recommendation is to use one of the many really good third-party HALT laboratories out there. But of course, a lot of mistakes are made when when people interact with these third parties. They simply just ship them something and say, "Tell us what's wrong." What you really want to do is be heavily involved with the HALT laboratory. When they will usually want to sit down with you and work out what the profile is going to be. What are your concerns about the thing you want them to test, etc., etc. And when you do that, that's when you get some really useful results. You're often invited on site if you want to turn up and watch your thing slowly dematerialize in front of your eyes.
All that work.
To work out. Yeah, it's actually an interesting topic, because a lot of people don't like HALT because it's not explained to them well. And engineers and designers and technicians can often be very emotionally attached to this amazing little device they've created. And when you say, thank you very much, I'm going to take your device and we're going to watch it break very slowly, or very quickly actually, it can be a little bit devastating. So often if you want HALT to work, you need to let people know up front before they start designing it, so they've gone through their grieving process before they get attached to it. And then all of a sudden, they know why you're doing it. They know how it's going to benefit them, and they're invested in it. A lot of organizations actually try and spring it on people at the last minute, and then you have to have a sort of soul-searching tour to explain why this is a good thing.
So one of the things that's a little different about a HALT test, in my mind anyway, is we run other types of tests, and the object is to make sure the part does not fail.
Yeah.
That's the object. If the part fails during whatever test we're performing, then that's a failure. In HALT, the object is to make the part fail. There's no such thing as like passing a HALT test, right? The object is just keep turning up the stresses until you reach a breaking point. And so it's a little bit different mindset. And so now we know every part that goes into a HALT test chamber will fail. That's the goal. In fact, it's a failed test if it doesn't fail, right? We've reached the limits of the tester. So how would one then interpret the results since all parts fail? How would one go about contextualizing the result of that? Again, my MacBook Pro will fail if I put it in the water. Apple's fine with that because that is well out of their intended use. They don't sell these things for scuba divers. So they're not worried about that. So that to them, if HALT subjected it to a underwater test, it would fail. And that would not be a surprise to Apple. They wouldn't change their design criteria. How do people not immersed in the world of reliability, people who are just trying to make a good product and are relying on a lab to give them test results, how do they interpret those results to incorporate, if needed, any design changes and things like that? How do they know that their part will survive in every conceivable practical use, even though it failed in a HALT chamber under a more extreme condition? Does that question make sense?
Yeah, but I think there's a sort of a whole genre of answers for that question. I think that let's just say if you want HALT to work and you haven't done it before in your organization, you really need to train people, or you really need to teach people what HALT is all about. You really need to not just direct them to do it, you need to convince them that it's going to benefit them to do it. And from a very selfish perspective, in a way, like the example I went through in my webinar, the point I was trying to make is that once you work out what the weak points of your PCB are, the changes you need to implement are fast, simple, and free 9 times out of 10. And so one of the mindsets we often need to defeat is, okay, so we need to do a business case, formal or otherwise, every single change, because the design change is going to cost this. How many failures are we going to prevent by doing this, et cetera, et cetera, et cetera. You go, no. The intent is to do this so early in your production process, your design process, that those corrective actions are fast, simple, and free. So we can do tons of them without having any appreciable effect on schedule or budget, because we're embedding them in either the first design or the second design. So that's one of the very first things. One of the things we also talk about is a HALT test cannot change the state of your product. So there's no point turning up the temperature until parts on your circuit board start melting, because that changes the state. Using the analogy or the example you use with the MacBook going into the pool, that not necessarily changes the state, but it just represents such an excursion out of what's going to be experienced. You're not accelerating life, the accumulation of damage. You're introducing a completely unique set of damage. So you have to make sure that the state of your system doesn't change. A melting is a very basic example, but there are things like eutectics and things like that, where if you increase the temperature of certain alloys, their microscopic structure changes, and therefore they won't behave in the same way as they will when they're being used by a customer. And so there has to be some understanding of the way this thing is likely going to fail in the hands of your user and customer, because you don't want to conduct a HALT test where you submerge your laptop into said pool. But you also need to convince the design team that we're not going to introduce non-representative damage. We're just going to greatly accelerate it. And if they're not bought into that concept, they're not going to be invested in the corrective actions. So they just need to be convinced that this is going to accelerate the likely ways this thing's going to fail in the hands of the user or customer. And you get enough of these things and you'll have enough opportunity and time to have as many fast, simple, free corrective actions as possible. And you don't know the effect of each one. But the idea is that you have enough of these fast, simple, and free corrective actions that they will combine to prevent the overwhelming majority of those failures that are likely going to occur, or at least delay them long enough for you to be a market leader in terms of reliability and perceived quality. I don't know if it goes anywhere near the zip code of your question, Mike, but
No, it does. That was a very broad question that would require an entire episode just to answer. So, you definitely hit it. Yeah, within the HALT testing, there's a couple of benchmarks that are referred to. One is operating limits and one is destruct limits. And during the testing, one determines the lower operating limit, the upper operating limit, and the upper and lower destruct limits. Tell me what the differences between operating limits and destruct limits are, and the importance of differentiating the two, and what the takeaways from those are.
Right. So the operating limit is a measure of stress, or the boundary of stress beyond which your thing won't work anymore. But let's just say it's temperature. Maybe your thing stops working at 125 degrees Celsius. The idea is that if you let it cool again, it'll come back to life. Destruct limit's very different. It's the limit where you get to a certain point, and even if you let it cool back down again, it's not coming back. So the operating limit tells you when and where your thing stops working in terms of vibration or temperature. For temperature, you have upper and lower operating limits, upper and lower destruct limits. And for vibration, it's just simply operating limit and destruct limit. There's no lower limit for vibration because it's always a positive value. Now, the main purpose behind these limits is to demonstrate an increasing robustness in your component when you go through an iterative approach to HALT. So, for example, PCB prototype number 1, you throw it in the HALT test chamber, and you come back with these list of weak points, this capacitor over here, we've got dendritic growth over there, whatever it is. And then you go away, redesign the PCB, get another prototype, and you put the next generation of the prototype into the HALT test chamber. What you want to see is the operating limits becoming broader and broader, and the destruct limits becoming broader and broader, because that just demonstrates that your thing's becoming more robust. In practice, I don't think either mean a lot in the real world, because you're not measuring temperature extremes or anything like that in a particularly scientific way. Same with vibration. It's just primarily there to demonstrate improved robustness and reliability through successive generations of HALT testing. As a rule, you can't read too much into those limits, but they're very important to give you internal engineering confidence that what you're doing is on the right path.
Excellent. How long does a typical HALT test take? If one had access to a test chamber through a third party, or if they had their own, what's the amount of time? Is it thousands of hours? Is it tens of hours? Is it minutes? If there's such thing as a typical time?
Less than an hour in many cases. There's actually lots of well, I shouldn't say less than an hour, it's less than a day. There's lots of different profiles out there which are trying to accelerate HALT testing even more. One profile in particular just involves temperature cycling. And the temperature cycle goes from one extreme to another extreme. Then slightly higher extreme, slightly lower extreme, then an even higher extreme, then an even lower extreme. The whole time vibrations are increasing as well. And the intent is for that to really increase or decrease, test time. That those accelerated profiles can be in the order of hours. So we're talking about a very, very short period of time in the overall production process. That's one of the overwhelmingly appealing parts of HALT.
I guess that's
so
the
fast.
H in HALT, highly accelerated.
Yes, highly.
Right?
Yeah, so if you look at the schedule of whatever it is you're trying to do, it's essentially instantaneous. A couple of days here. In fact, posting or mailing your device to the laboratory is probably going to take longer than the test itself. So we're talking about very short time frames. You're not trying to quantify how reliable your thing is. That's not what HALT's all about. That's HALT and other things. But so we're talking about very short periods of time in order to get that information as quickly as possible without having to waste too much time. The more time you waste, the less likely it is for those corrective actions to be fast, simple, and free.
Well, that's a whole lot better than some of the testing we're doing in our industry. Right now, we conduct, in order to comply with one of our trade association's standards on cleanliness, we have to run a surface insulation resistance test, or SIR test, under heat and humidity conditions for 172 hours. That's the minimum.
Right.
And, so there's a week of your life you're never going to get back, right? And then if it fails, then you have to figure out why it failed, remedy the problem, and then start the clock over again. So for an hour or so, or a day even, that's pretty good. If one subjects a product to HALT testing, and then they get the results, and those results require maybe a redesign of, rubber pads, shock mounts, to reference your example, or using a connector for a wire instead of a soldered wire to a board, whatever the case may be, or stress reliefs. Is it then a normal practice to retest the assembly to establish new upper and lower destruct and operating limits, or is that overkill in your experience?
There's no right or wrong answer. A lot of organisations, especially if they have longer times, so if they have production, they will certainly do that. That very fast test profile I was telling you about, that sort of 5-hour thermal cycling coinciding with vibration steps increases, there's no, that sort of test doesn't involve an upper or any sort of operating limits or destruct limits, because both things are being conducted at the same time. And so it's just simply a best guess at the prioritised weak points. But there's also engineering judgment to be involved as well, because if you look at the weak points as suggested by the report you get from that third-party HALT laboratory, if you are very comfortable, you've designed them out of your component or your product or your device, and that the design changes have not of themselves introduced a whole new suite of stresses, which is a very important consideration, it's not necessarily wrong to say we're good, because now that part of your system might not be the most concerning part of your system anymore. It might be something else, and if you have another part of your system, they're doing HALT and they're really struggling to get meaningful changes for whatever reason, then they're the ones that should get the whatever budget you have for HALT moving forward. So there's no right or wrong answer, but there's plenty of scenarios where it makes sense to have this multiple generation of HALT tests going on, so you can see hopefully improvements in the destruct and operating limits. There's also plenty of scenarios that just make sense to do it once and be comfortable that you've made some good changes.
Sure. And I think the supply chain shortages have demonstrated that when someone substitutes a part for another similar operating but different type of part, it can create a domino effect. It may cause a problem on an adjacent component or area of the product. So, by putting in a connector instead of soldering the wires to the board, for example, all of a sudden, the connector now is subject of potentially the subject of HALT testing. The connector may have its own unique criteria that it likes to operate in. So we may solve one problem, create another. So I guess that in theory, even there's really no end to testing, because every time you change, you address the results of the test, you're almost justifying another test again, and which may then, I guess the only time you don't have to is if the results are satisfactory, no engineering changes, everything is good. We're almost out of time, so let's just end on a couple of more philosophical questions. We'll get out of the HALT test chamber, and we'll kind of go up to the clouds. You talk about the importance of having a reliability mindset. Tell me more about what you mean by that.
Well, there's three parts to what I call the reliability mindset. One part is a clear understanding of value and what that means to your organization. And within that overarching remit, or that overarching edict, let's call that, the concept of value needs to be discussed with the language and then generated through methods. HALT is an example method that can hopefully generate value for you by giving you the prioritized list of weak parts of your prototype, which you can then design out of your system. Too many times, reliability engineers and quality engineers just follow the bouncing ball, tick the box, and confuse effort with outcomes. Use the wrong terms, confuse, for example, MTBF with warranty reliability and servicing intervals and all sorts of nonsense like that. So one of the very first things you need to do is get the language right for your organization. So you use warranty reliability and not MTBF, or you insert the appropriate definition here. And then once you have a good idea of what it is that makes how you generate value for your organization, and once you got the language right, then you start talking about what it is you're going to do to get there. Is HALT testing the right thing for you? It might not be, and I can't tell you if it is or if it's not. But if you have the language and you understand what, for example, the difference between HALT and ALT is, you're well on your way, if you have a good understanding of what value looks like for your organization, to make a judgment call about whether HALT is the thing you're going to use or not. Many organizations who do reliability well tend to focus on one sort of central activity in their philosophy and do that really, really, really well. Some organizations, it's all about FAMIRs. Some organizations, it's all about HALT. Some organizations, it's all about fault tree analysis up front. And none of those things are wrong if they're done well and they mostly suit the industry in question. So the reliability mindset is all about trying to work out, using correct terms, the correct language, understanding how every single decision you make generates value and how it's going to be informed by a method, a reliability engineering method. If you don't have that mindset, if you don't have that inquisitive mindset, you just keep doing what textbooks and standards and, old greybeards say you should do. But the problem is that things are moving too fast for you to have any sort of relevant outcomes if you keep using yesterday's solution to a problem which probably has already been solved. So it's all about understanding what it is you're trying to achieve, and never stop questioning and finding the vital few weak points of your system to design out.
Yeah, excellent. And finally, your company is Acuitis. Tell me more about Acuitis Reliability. What does it do? What services does it perform, et cetera?
Well, last time we spoke, probably the answer would have been a very, breakdown of consulting and training. Actually, what I'm doing right now is I'm sort of that whole pandemic thing you referenced at the start of today's chat.
Yes, yeah, those days, yes.
It's actually pushed me into training. So what I'm actually doing right now, just hold on, is I'm actually generating lessons and courses using avatar instructors, so a digital clone of me, and it allows not only the courses to be, really well scripted so that there's no ums and ahs, but have, really focus on explaining key messages as simply as possible, and of course being able to translate that really easily into different languages. And then also allows me to really easily update courses, or allows us to update courses when a student says, hey, third minute of lesson number 4, these words didn't make sense. We go change the script, and within a week or so, the video's now that much better. So that's the sort of focus I'm doing these days. And some of the some of the content you saw in that webinar will be embedded in some of these courses moving forward. So that's our main focus these days. It's a brand new world out there using.
Chris Jackson has joined the metaverse, right? And
right,
you're in there now. You've been digitized.
Well, my avatar instructor version of me, he says that he's a better version of me, so we need to have a chat between him and me. But I mean, the idea is that it allows us to get some really high quality training going on without having to try and nail it one time every time. The problem with traditional training is that if you film it, for example, it's not much. It's just not cost efficient to go back and change little bits here and there.
Right.
But avatar instructors allow that.
Yeah,
and allow you to have a perfect script, so to speak.
Right. It can be changed on the fly. You could change
one
acronym with a few keystrokes and not have to get the Hollywood production crew out and the editing crew out and all of that. If my audience, if you would like to get more information on Chris's company, I will provide that information in the show notes. If you are listening to this on your favorite podcast app, once it's safe and you pull over, don't do it while you're driving. Go to your podcast app, look at the show notes, and you can get information on Chris's company. Also, if you're watching this on our Reliability Matters YouTube channel, right down there it says Show More. Click that, and you will also get information on Chris's company, Acuitis Reliability. And maybe if you're interested, you could experience the avatar, which is, I guess, far better looking and smarter than even Chris Jackson is, right? That's what the avatar thinks anyway, or that's what Chris told us to think.
It's a digital clone, so it looks exactly like me, unfortunately for it. It'll have my voice perfectly cloned as well. Technology's pretty good, but anyway, he's much better at getting the words right first take every time.
I've been playing with an app. I'm not sure if I'm going to use it yet. It's for, obviously to do this content creation, you do a lot of editing, right? And it's a kind of a very specialized for podcast editing app. And one of its kind of side features is you can type in a script or import a script, and it will read it in your voice. And it does a pretty good job at mimicking your voice. There's still some inflection differences because they haven't quite got inflections down. If you're Canadian, you end every sentence with a high note. That's just the way they do it there. And if you're from different parts of the world, certain inflections are different. Maybe you intentionally want to inflect something different. And I don't think it's quite got that down yet, at least natively. It can be trained, but it's pretty good. So I don't know if I'll ever do an avatar version of me. Maybe if I go on an extended vacation, I'll take advantage of digital mic, but I don't know. We'll see.
Well, the technology is improving so rapidly that the avatar version of you 2 months from now will be that much better than the avatar version of you today. So it's a brave new world, but essentially the ability to perfectly script and rework and try and really distill the key message into a simple language as possible. That's the main attraction about using avatars, and scientific studies actually show that avatar instructors are often giving better outcomes.
We call it avatars and voice duplication, and in the nefarious side of the internet, it's called deep fakes. Right? It's kind of the same thing. It's a deep fake Christopher Jackson, only it's more like deep real as opposed to fake. Well, Dr. Christopher Jackson, thank you once again for coming back to the show, the reprise of Dr. Chris. And thanks for explaining to me and my audience a little bit more about HALT and reliability in general. I really appreciate your knowledge and your willingness to spend the last a little over an hour with me and my audience and sharing that knowledge.
It's been a pleasure, Mike. Looking forward to the next time.
All right. But how will I know it's really you? It could be your avatar.
You'll be... With all the pauses and ums and ahs, you'll be able to quickly work out that this is the first generation version of me.
If it's too perfect, it's not you. All right. Well, thanks, Chris.
Definitely.
It's good to see you again. Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Our podcasts have been downloaded more than 35,000 times, and I remain ever grateful for your support and encouragement. Don't miss an episode. Listen and subscribe to the Reliability Matters podcast on your favorite podcast app, or watch it on the Reliability Matters YouTube channel. If you're watching this on YouTube, be sure to click the like, subscribe, and bell icons to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of each month. A special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks for your questions and episode suggestions. Please keep them coming. You can send them to my email address, mike@mikekonrad.com. Just remember, that's Konrad with a K. Once again, thanks for listening or watching. Until next time, stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.